Hello and welcome to my presentation about laser-based hair crack detection on wafers. This is collaborated work between Robin Priwald from BRS Systems, Franz Bernkopf from TU Graz and me, Alexander Fuchs, also from TU Graz. The data required for this paper is acquired using the wafer edge screener. The wafer edge screener is a laser-based wafer inspection device developed by BRS Systems. It is a small device and can be easily integrated into existing production infrastructure and can be used for optimizing and monitoring production processes. The wafer edge screener measures the wafer by rotating the wafer through the device as multiple laser diodes in combination with a CCD array record the geometric signature of the wafer edge. Each of the points on the wafer edge is represented by a separate channel in the measurement device. The wafer edge screener can detect defects in the green area. Defects closer to the center of the wafer cannot be detected. So what can you use the wafer edge screener for? You can use it for quality control of the critical processing steps. You can use it for incoming and outgoing control. You can use it to optimize your processing steps and improve your yield. And of course, as I said, you can also fit it into existing production infrastructure. What are the benefits of the wafer edge screener? The wafer edge screener is mostly material independent, so you can measure various kinds of materials, reflective materials, transparent materials, without having to change settings on the device. Additionally, we can also measure strongly warped or misaligned wafers due to our robust measurement principle. Let's talk a little bit about the specifications of the device. The device can achieve a noise floor of down to 1 micrometers and achieve an absolute positioning accuracy of 20 micrometers. For our task, the task of classifying defects, the most relevant specification is the relative accuracy. So relative from time measurement to time measurement. And this device can achieve a relative accuracy of about 2 micrometers. My part in this project is the implementation of embedded AI modules. The target is to achieve a good localization and classification of defects within the measurement data. And we want to solve this task using a deep neural network with limited complexity, since standard methods cannot deliver good results on our data. For this paper, we would like to evaluate the hair crack detection capabilities of our system. So first of all, I will talk about why is hair crack detection hard or harder than detecting other kinds of defects. Then I will present the kind of time series data that we use, and I will explain why we want to use pre-processing feature instead of the raw input data. Then I will go into more detail about our proposed features and what is the motivation behind each of them. I will explain the kind of deep neural network that we use for our classification task, and I will present some experiments and results. So let's talk about our measurement data. For detecting and classifying normal defects, it is sufficient to use the upper and lower edge information calculated using all n measurement channels on the wafer edge. This can be used for detecting flats, notches, or defects such as chips, cracks or breakouts on the wafer. For detecting hair cracks, we need to use the full information available. Since hair cracks, as you can see on the right, only cause a very small geometric signature in the signal. On the other hand, hair cracks have the advantage that the crack goes through the whole wafer. Therefore, we can use the correlated information of all channels to engineer specialized features to extract this correlated information. Why do we even want to use pre-processed features? In deep learning, It is quite unusual to use engineered or specialized features, since we assume that the network can learn good features by itself during training. Since we are limited by our network size due to runtime issues on the embedded device, we want to present the data in the most efficient way possible. Therefore, engineering good features can free up network capacity to learn the classification task. The good thing about hair cracks is that they cause a very unique signature, and we can come up with very efficient features for our networks. Additionally, these engineered features will not contain the whole information of the measurements. Therefore, we want to add some additional information providing the upper and lower edge channels, so the network can take this information into account for its classification. So let's start with our proposed features. Our features try to reduce the input dimension from n channels to one channel, leveraging the unique behavior of the hair cracks. This means that hair cracks cause a jump in the signal at one angle and across the whole wafer, which is present in all channels. We will consider time and angle equivalent, but for the sake of simplicity, we will now only speak of time. First, we take the signal derivatives of all channels. Since the signals jumps might not be aligned among all channels, we additionally apply a running average over the channels. We use variant R, which uses a standard running average with window size M, and variant S, which uses a weighted running average, where the weights W are learned during training. Now that the channels are aligned, we can come up with our first class of features, which are the product-based features. Here we take the product over all channels, which causes a steep jump in the signal. We add 1 to the average signals in case one channel drops out or has zero derivative. And we subtract 1 again to center the signal around 0. The second class of features are the correlation-based features. Here we sum over pairwise products of features. This provides us with smoother features than the product methods. For feature 3 and 4, we don't only sum over the off-diagonal elements of the correlation matrix. And for feature 5 and 6, we also include the main diagonal of the correlation matrix. This takes more emphasis on the amplitude of the signal. The last class of features are the mixed features. For the mixed features, we first normalize both the product and the correlation component, and then we add both components. We use a batch normalization to normalize those features. Feature F7 consists of the normalized features F1 and F5, which use the normal weighted averaging, and feature 8 consists of F2 and F6, which use the weighted averaging S. The mixed features combine both benefits of the product and the correlation methods, which are for the product methods that they have a strong amplification of correlated features, and for the correlation methods that they are less sensitive to alignment issues. All features are again normalized using a batch normalization, including a scale in the shift parameter before they are fed into the network. Let's start with the neural networks. In time series analysis, there are generally two approaches: recurrent neural networks and convolutional neural networks. Recurrent neural networks process the time series time step by time step, and the information is passed on between the states. In convolutional neural networks, the time series is split into different frames, and the frames are analyzed separately. Therefore, no information is exchanged between the frames. If we want to do time series analysis, we need to provide an overlap between the frames. Our method tries to combine the benefits of both approaches. We try to reduce the computational complexity by utilizing the parallelism of the CNNs, and we try to achieve a better classification performance by passing on information between the frames. The CNN tries to capture as much information as possible on many timescales using dilated dense kernels. This information is then extracted, and the RNN passes on the information from frame to frame. Therefore, the network is able to provide a better prediction using the past information of the other frames and the information of the current frame. This method has the advantage that we do not need any frame overlap, and we can provide a prediction for every time step without having a prediction delay. Let's have a closer look at the network. The network consists of three main blocks: the frame block, the RNN block, and the FNN block. The frame block has a CNN using dilated dense blocks. Each of these dense blocks consists of convolutions which are dilated. This means that as the depth of the network increases, the layer or the kernels get more and more dilated, capturing information on different timescales. The next block is the RNN block. The RNN block extracts the average information across the time axis and uses this information to update its state and pass on the information to the next frame. In the last block, the FNN block, the information on the time step level from the CNN and the information between frames from the RNN is cast into a single prediction for each time step in the frame. The next point is the experiments. Our experiments focus on small networks with around 26,500 parameters to limit the computational complexity of the model in order to run on the embedded device. We will be evaluating the F1 scores across our proposed feature variants using no context information, and then again using the context information provided by the upper and lower edge channel information. Also, we will be evaluating the performance across different hair crack magnitudes. We will take the F1 score as our measure of success. The F1 score is a combined measure analyzing the false positive rate as well as the false negative rate. Our dataset consists of multiple original measurements. One measurement corresponds to a full wafer rotation. The data includes flats, notches and defects such as chips and cracks, but it does not include any real hair cracks. The hair cracks are generated solely artificially by using a smooth step function. The hair cracks for the first experiments are sampled from a magnitude range of 2 to 20 micrometers. We generate 3,100 samples using data augmentation techniques such as signal inverting, the changing of channels, and also mixing different kinds of signals. For these experiments we use a test set with about 450 samples. For the experiment evaluating the different crack sizes, we generate 5 test sets using about 400 samples. Now in the first experiment, using the hair crack sampled from 2 to 20 micrometers, we compare the performances of our proposed features to the raw input data G. The raw input data achieves about 81.77%. On average, our proposed variants achieve about 95% F1 score. In the table, we can see that most variants perform the best using an averaging window of about 10 time steps. The best variant is variant 8 with an averaging window of 15, achieving an F1 score of 95.32%. In the picture on the right, we can see that the gap to 100% mainly originates from the false negative rate. This means that the network is not able to detect these samples. But we can see that we do not predict many false positives. For the next experiment, using the same dataset as before, we add the upper and lower edge information to restore some of the information which we assume is lost during feature preprocessing. Surprisingly, also our baseline variant using the raw input information can improve substantially. Most of our proposed feature variants also improve the results. Here the best variant is variant F2, using an averaging window of 20, achieving an F1 score of almost 69% across the range 2 to 20 micrometer. Comparing the F1 scores of the networks using the additional lower and upper edge information and not using this information, we see that most of the variants using the additional information can outperform their counterparts. Therefore, we assume that this information is valuable to the network and can improve the performance of the hair crack detection. In the last experiment, we evaluate the network's performance on different magnitude ranges for the hair cracks. All of the networks were trained with the standard dataset using hair cracks from a range 2 to 20 micrometers. We see that most of the networks perform quite well until a crack magnitude of about 4 micrometers, with the best variant being feature variant 8, achieving an F1 score of almost 97%. Surprisingly, feature variant 7 even achieves quite impressive results for 2 to 4 micrometer hair cracks, which are already very close to the noise level of the device. But there seems to be a trade-off between detecting very small hair cracks and the overall detection performance of the network, since variant 7 does not perform that well for the other magnitudes of hair cracks. Therefore, it is a design decision on whether the network is specialized on detecting very small hair cracks or achieving a good overall detection performance. To summarize this paper, I first introduced the wafer edge screener to you, which was used for recording the time series data for this task. Then we did some analysis of the input data. I proposed some specialized features which leverage the geometric signature of the hair cracks. We introduced the used DNN architecture, and then we presented some experiments evaluating the performance of the proposed features with upper and lower edge information and without upper and lower edge information. At last, we also did some experiments evaluating the performance of the networks across different crack magnitude ranges. In conclusion, we can say that using the correlated input information of all input channels, we can detect hair cracks with a quite high confidence. We see that our proposed features can substantially outperform the baseline variant using the raw input data, and also we see that upper and lower edge information can provide valuable information to the network, improving the detection performance even further. Generally speaking, we can say that using our deep learning methods, we are able to detect hair cracks down to a magnitude of 4 micrometers with a very high confidence, achieving an F1 score of up to 96.95%. This is an impressive result considering that our resolution is only about 2 micrometers. In the future, we would like to evaluate our networks on real hair cracks. We would also like to combine this network with the detection of other defects, and we would like to apply some techniques to make the neural networks even more efficient, such as neural architecture search, pruning, or quantization. Thank you for your attention. If you want to know more about the wafer edge screener, please feel free to get in contact with my colleagues from Bright Red Systems. Goodbye and have a nice day.